basically, we have seen that Young's modulus was the ratio of normal stress to the longitudinal strain, right?
Yes,
Now
ma'am.
see, we have another type of modulus of elasticity. The first one we have discussed, Young's modulus. Another one we have is known as shear modulus, or this is also known as modulus of rigidity. This modulus comes into action when there is a change in shape. When there is a change in shape. For example, the rectangle which you are seeing with the continuous line is the original shape. Now I have applied a parallel force. Now there is a change in this. It has shifted to some delta L length with the initial length as its L, which we have already seen when we have discussed shear strain. This is the area of the cross. This is the area of the upper layer. This is the area of the section. Now see, the way we had Young's modulus was the ratio of normal stress to the longitudinal strain. If the ratio is between the tangential stress and the shear strain, then that particular modulus of elasticity is known as shear modulus or modulus of rigidity. So basically, modulus of rigidity is represented by this symbol, eta. So eta is equal to tangential stress divided by the shear strain. In case of Young's modulus, we've seen that this stress was normal stress. And we've seen that the strain was longitudinal strain. Now, in case of shear modulus, the stress is tangential stress and the strain is the shear strain. So see, the formula for the tangential stress is also known as shearing stress. So you can write this as shearing stress by shear strain also. So shearing stress, as you've told me just now, that the formula for stress is force upon area. So if F is the applied force in this direction and A is the area of this object, then shearing stress should be force upon area. Similarly, shearing strain, this we have already discussed yesterday only, shearing strain. Do you remember the result which came? We took out this triangle, we rotated the figure, calculated tan theta.
To delta L by L.
Delta L by L, yes, delta L by L. So we can conclude that shearing stress by shearing strain would be equal to F by A to delta L by L. And if you write it on simplification, it would be FL divided by A delta L. This is the formula for shearing modulus shear strain or modulus of rigidity, shearing modulus. And again, since it's a modulus, it's one of the moduli of elasticity, the SI unit would be same, which we have discussed in detail yesterday. Because this is a dimensionless quantity, the unit would get cancelled. The only unit that would remain would be for force and area. So that is Newton per meter square. And 1 Newton per meter square is equal to 1 Pascal. Fine. Just note this and we'll do some numericals on it.
Done, ma'am.
I'm giving you a numerical. Just try that. Tell me the answer. See, this is the side of the cube given, and its upper face has been displaced by this much amount. The tangential force which has been applied is this. Now you have to find out the modulus of rigidity. And while calculating, just check that all the quantities are in their SI units. Yes, Hishma, did you try the question?
Ma'am, I'm doing the calculation part.
Do you need 1 more minute or shall I explain you?
Ma'am, I'll do it.
Okay. Okay, Hishma, at least tell me the things which are mentioned in the question. For calculating modulus of rigidity, this is the formula FLA divided by delta L, similar to the Young's modulus. It says that the upper face has been shifted. It means this portion has now been shifted. So this is the change which it is referring to as 0.2 centimeter. You just tell me what are the values given for these things. Like what is the force given? What according to you is F?
8 Newton.
8 Newton. What is L? This L length.
0.05 meter.
Yes, 0.05 meter. What is A?
6 into 0.05 whole square.
6 into 0.05 whole square. Why?
Because we have to find the area of the cube.
No, see. That's what I was telling you, that the area is the area of this upper layer. Fine. So this 6 won't be there. If you multiply it with 6, that would give you the whole area of the cube. Yes or no? Area is basically L square. If you have to find out the area of this portion, one face. Okay, so area is the upper faces area only. And what is delta L?
0.2 centimeter.
0.2 centimeters. Or you can say 0.2 into 10 to the power minus 2 meters. This is in meters square. Fine. Now do the calculation.
Ma'am, is it 8 into 10 to the power 4?
8 into 10 to the power 4 Pascal. Yes, are you saying this?
Yes, ma'am.
Yes, it's correct. Absolutely, this is the answer. Correct. I think initially you must be committing error while multiplying it with 6. Just remember, you have to calculate the area of the upper face, the face which has been displaced or which is being displaced. All right.
Yes, ma'am.
Okay, I'll give you another question based on this formula only. Just try that. Yes, Hishma. See on the screen now. See, the question says that the two strips of metals are riveted together at their ends by four rivets. It means if these are the two strips of metal, let's say first green one and then another red one, there are four rivets like this. Both of them have been stuck together. So let's say F is the force applied. F is the force applied on the metal strip. Now, if F is the total force applied at this section, can you tell me what is the force on each rivet? Yes. If the force applied on all the four rivets is F, can you tell me what is the force on each rivet?
F by 4.
Yes, exactly. It would be F divided by 4. Now, for each rivet, which we have, for each rivet, the shear modulus would be equal to shearing stress divided by shearing strain. Shearing strain. Now see. Now can you tell me what is the stress on each rivet? What is the stress on each rivet? What is the formula for stress we have? Yes, sir. On each
F
rivet,
by 4
F by 4
into area.
into area. Exactly. Because force upon area is the formula for stress. And if we have to calculate for each rivet, then that would be force on that particular rivet to the area. So that would be force divided by 4A. Then maximum stress that is given in the question to us is maximum shearing stress is given 2.3 into 10 to the power 9 pascals. Yes or no? This is the shearing maximum shearing stress which should not be exceeded. So maximum stress on each rivet, that is F by 4A, should not exceed what value? 2.3 into 10 to the power 9. 9 or 11? 9.
9.
So 9. 2.3 into 10 to the power 9. So this is our stress, maximum stress. And this is what we have calculated according to the question. Now what should be the force? The question is asking you this force only. So this force is 2.3 into 10 to the power 9 multiplied by 4 into area. Now for the area, for a rivet is the end of the cross section of the rivet is a circular surface. So the area should be pi r square. Do we have the radius of each rivet with us?
We have
Yes,
diameter.
we have the diameter, exactly. The diameter is 6 millimeters. So the radius should be, if diameter is 6 millimeter, radius should be
3 millimeter.
3 millimeter. Yes. So this would be 3 into 1 millimeter is 10 to the power minus 3 meters. So 3 millimeters would be 3 into 10 to the power minus 3 meters. So we have value of everything. So the force once we'll calculate is 2.3 into 10 to the power 9 into 4 into area. For area we have pi r square. Value of pi is 3.14 and r squared. 3 into 10 to the power minus 3 whole square. This much Newton is the maximum tension that the question is asking. Just note this down, then we'll move further.
Ma'am, can you scroll down? Done, ma'am.
All right, see now how much we have covered. We have completed the Young's modulus of elasticity, which said that it was the ratio of the longitudinal stress to the longitudinal strain, means the normal stress to the normal strain. Now then we have seen this modulus of rigidity or shearing modulus, which says it is the ratio of tangential stress to the shearing strain or shearing stress to the shearing strain. Now see, we have another type of bulk modulus for this. See, bulk modulus is defined as the ratio of normal stress to the volumetric strain. Okay, let me erase it for you, then it would be clear. Just wait. See, this is the sphere. Okay, all right. So V is the original volume of the sphere. The original volume of the sphere is V. Original volume. Now all these deforming forces have been applied and it has compressed the sphere to this V dash. V dash is now the new volume. V dash is the new volume. So there has been a decrease, a change in this volume, this much portion. So delta V is the change in volume. Change in volume. So bulk modulus, or sometimes it is represented by K, but let us take it as B. B is the bulk modulus. So bulk modulus is the ratio of the normal stress, this perpendicular force that has been applied per unit area, normal stress But the strain over here is the volumetric strain. Volumetric strain. Fine? Now see. Now what is the normal stress? What is the formula for normal stress? We have discussed this several times. What is the formula for normal stress? Yes, say
Force by area.
force by area. Normal stress is force by area. And volumetric strain. Strain is always change in dimension by original dimension. So since volume is changing, volumetric strain would be change in volume, that is delta V, to the original volume. So from here we can infer the formula for bulk modulus. So it would be F, this is F by A, so F by A, and this whole term in the denominator, delta V by V. Now see, since the volume is getting compressed, this was the initial volume, now the final volume is lesser than the original volume. So we put a negative sign so as to show that there's a decrease in volume. So in the volumetric strain, you can also add a negative sign. This negative sign indicates decrease in volume. And what is force upon area? Force upon area is also known as pressure. So you have another term for bulk modulus. One is this. But if you put in pressure instead of force upon area, this would give you minus PV. Instead of F by A, you're writing P minus PV divided by delta V. This is another formula where P is the pressure. So remember that bulk modulus for solids, for solid object, is greater than bulk modulus for liquid object than bulk modulus for gas. So solids has the higher. And again, the SI unit would remain same, Newton per meter square or Pascal. The SI unit is same for all the moduli of elasticity. We have another term known as compressibility. We have another term known as compressibility. So compressibility is basically the reciprocal. Compressibility is basically the reciprocal of this bulk modulus. Compressibility of a material is a measure of how easily the material is compressed. So in other words, you can say compressibility is just reciprocal of bulk modulus. So I can write compressibility. The compressibility factor is actually reciprocal of bulk modulus, means 1 by bulk modulus. And let us represent this by K. And we represent bulk modulus by B. Usually, we are taking this. So K would be equal to 1 by B, the reciprocal of bulk modulus. So since the SI unit of bulk modulus is Newton per meter square, the SI unit of compressibility, would get inverse. It means it would be 1 by Pascals. That is Pascal to the power minus 1, inverse. Or you can even write it meter square per Newton, or Newton to the power minus 1 meter square. The rest just the reciprocal of whatever you have learned about bulk modulus. And since the comparison of bulk modulus for all these three states of matter was this, it would get reciprocal or it would get reversed for compressibility. So K, the order K would be this. For solids, it would be the least now, because it's just reciprocal of bulk modulus. So solids and liquids are relatively incompressible. That is, they have small values of compressibility, K, or you can say large values of bulk modulus. And these values are almost independent of temperature and pressure. Right, just note this, then we'll move further.
Can you scroll down? Done, ma'am.
Is the screen sharing with you?
No, ma'am.
It's not sharing. Just a second. Is it sharing now? It's still
Yes,
not visible. Is the screen visible or not, Hishma?
yes, ma'am, it's visible.
Okay, fine. Now I'm giving you question based. Just try that. See, just in case you don't know, we'll be discussing that in fluids. Pressure by a water column. Pressure of water column is given by H rho g. Means height of the column, density of the liquid into acceleration due to gravity. If you need this, you can use it in the question. Do you know the density of water? Yes or no? Or shall I tell you? Yes? What did you say?
No, ma'am.
Okay, see, for calculating for calculation of the pressure, you will be needing these three things. So height is already given in the question that the average depth of the Indian Ocean is 3000 meters. For density, density of water is 1000 kg per meter cube in the SI unit. And acceleration due to gravity. Do you know the formula, the value of the acceleration due to gravity?
9.8.
9 point
9.8.
9.8. But in this question, just take it as 10. 10 meter per second square, and height is already given 3000 meter. And you already know the formula for bulk modulus now, minus PV by delta V. So you have all the quantities with you, all the numerical values with you. You just have to calculate delta V upon V. This portion you have to calculate. Rest, all the data is available to you. Now find the value of delta V by V.
Ma'am, is it minus 2.72 into 10 to the power minus 3?
Minus,
Minus 2.72 into 10 to the power minus 3.
no, not minus 2.7. See, now you have tried, now you'll be able to understand it better. This, you have understood the formula
Yes, ma'am.
or what we have to calculate, fine. Now delta V by V from this would be after cross multiplication would give us minus P by B. So let us take the modulus because minus negative sign only indicates that this shows that there is a decrease in volume. Decrease in volume. So let us put modulus and calculate the value. Because we already know that the question says it is fractional compression. So obviously there is a negative sign. Now see, pressure, for calculating the pressure, it is H rho G. So pressure is height is given 3000 into density is 10 to the power 3 and G also is 10. So pressure would be 3 into 10 to the power 7 pascals. Yes or no?
Yes, ma'am.
Yes. So pressure is 3 into 10 to the power 7 pascals. This is delta V by V. Now the bulk modulus. How much is the bulk modulus? 2.2 into 10 to the power 9. Bulk modulus is given to us 2.2 into 10 to the power 9. This is the bulk modulus given. Once you solve this, you will be getting the value approximately equal to 1.36 into 10 to the power minus 2. Did you write it till here? Is this statement written correctly in your notebook? This.
Yes, ma'am.
Then it's fine. There must be minute calculation errors which you'll be able to overcome with practice. Then that's okay. And if the question asks you what is the percentage change, then just simply multiply this whole term with 100. 1.36 into 10 to the power minus 2 into 100. So that would give you just 1.36%. If the question asks you for percentage change in case of this question, just do this. Okay, just note this portion. We'll do one more numerical. Did you understand this or not? I think you must have done just a little mistake over here in the calculation. Otherwise, if you've written till here, then that's fine.
Done, ma'am.
Let's do one more numerical. So just as to wrap this chapter. Just in case, again, if you need that formula, P is equal to H rho G. This will be in detail in the mechanical of fluids chapter. But if you need this, remember the density of water in CGS is, because all the densities are given in their CGS. So density of water is this 1 gram per centimeter cube in CGS. And in the SI unit, I have written it earlier in the previous question, that was 1000 kilometer, 1000 kg per meter cube. Sorry. Depth is given to you and compressibility is given to you. And this is per atmosphere. So 1 atmospheric pressure is also mentioned. Just try to find out the density. And since everything is given in CGS unit, do take acceleration due to gravity also in CGS unit. That would be 1000 centimeter per second square. Instead of 10 meter per second square, take it as 1000 centimeter per second square. Just do everything in CGS unit, because all the values are mostly in CGS. So convert this also into CGS only. See, at least calculate two things. Just tell me what is the bulk modulus coming and tell me what is the pressure. Rest I'll help you then.
Pressure is 3 into 10 to the power 6.
3 into 10 to the power 3 into 10 to the power what?
6 Pascal.
Not pascals. That's what I'm telling you constantly. You are right. You're near. You're very near to the answer. But just tell me CGS unit. So you have to have all the answers in one unit. If had the question been asking in SI unit, then we would have also told our answer in SI unit. Now the question says it is everything is in CGS units mostly. See, this is also CGS. This is also CGS. So you also take out the value of pressure in CGS only. You're very close to it. Just tell me these two things first. See, bulk modulus is very easy to calculate if you look at the question carefully, because compressibility is given to you. If you have the compressibility, you can calculate the bulk modulus.
Ma'am, bulk modulus is 1 by 0.00005.
Yes, 1 by 0.00005. So that would give you some amount of atmosphere. Yes, ATM. Just calculate the reciprocal. That would be, I think, 2 into something ATM. Then just convert ATM into this. Multiply that term with this. See, bulk modulus is absolutely right. It's 1 by 0.005. So that is 2 into 10 to the power 4. But that's ATM. Bulk modulus. Bulk modulus is reciprocal of compressibility. So that is 1.0.00005 as rightly said by you. So this would give you 2 into 10 to the power 4 ATM. Atmosphere, but we don't need the answer in atmospheric pressure. We need it in CGS unit. So just multiply it. So bulk modulus would be 2 into 10 to the power 4 into 10 to the power 6 with this unit. Dyne per centimeter square. Is the bulk modulus clear to you?
Yes, ma'am.
Yes. Now let us calculate other things as well. Now see, for pressure, you have the height as 3 kilometers. So the height is 3 kilometers. That is 3 into 10 to the power 5 centimeters, because we don't need the answer in meter or kilometer. We need the answer in centimeter. So 1 kilometer can be converted into 1 centimeter. So 3 kilometer would be equal to 3 into 10 to the power 5 centimeter. So now if you calculate the pressure from all the data given, that would be equal to 3 into 10 to the power 5 multiplied by 10 to the power 3, just for 1000. So this gives 3 into 10 to the power 8 dyne per centimeter square. Just a second. Yes, see, so 3 into 10 to the power 8 dyne per centimeter square. Till here, is it fine?
Yes, ma'am.
Okay. See, volume is given. We have to know the volume. So it was given in the density. We can find out it's 1 gram in 1 centimeter cube. So volume becomes 1 centimeter cube itself. Volume is 1 centimeter cube itself. I hope you know how we are calculating. If this is, let this be the depth. then we are calculating it for this much portion, which is 1 centimeter cube. And the height is given 3 kilometers. This much portion, right? So volume is this. Now we have all the data to calculate delta V, means change in volume. We have to find out this. So delta V would, bulk modulus is basically this. B, this. This is the formula for bulk modulus, yes. So delta V would be minus PV by B from the formula which we have studied. So delta V would be equal to minus PV by B. V is 1 centimeter cube. So delta V would be 3 into 10 to the power 8 multiplied by 1 divided by 2 into 10 to the power 10. So this would be approximately 1.5, 3 by 2. So delta V would be 0.15 centimeter cube. Is it clear how we
Yes,
have
ma'am.
got change in volume? Now see, final volume is equal to, the change in volume is basically final volume minus initial volume. So the final volume, this V dash, would be equal to V minus delta V. Yes. Now see,
Yes.
V dash would be, initial volume is 1, final, the change in volume we have calculated as 0.15. This gives 0.85 centimeter cube. This is the final volume. Now we have the volume with us. So I hope you know this formula. Density is equal to mass by volume. So density, the final density which we want to calculate would be, the mass is 1 gram. It was written na, 1 gram per centimeter cube. So mass is 1 gram and volume is 1 centimeter cube. And the final volume we have calculated 0.85 gram per centimeter. This is the final density. Understood or not?
Yes, ma'am.
Shall I repeat once more or is it fine?
It's fine, ma'am.
Okay, just note this then.
Ma'am, can you scroll down?